Every AI calculation generates real physical heat. In this explainer, we're diving into the invisible physics inside massive AI systems.
How do engineers control heat they can't even see? Well, to manage this hidden thermal weather, they use CFD.
CFD stands for Computational Fluid Dynamics. It translates invisible thermal behavior into stunning visual data to prevent catastrophic overheating.
Heat basically transfers in three main ways: conduction through solids, convection via moving fluids, and radiation across open space. Convection is fascinating. It's when fluid flow actually carries heat away from a warm server, pulling in cooler air.
Now, cooling systems force convection using powerful fans, but natural convection is driven entirely by gravity and density changes.
See, when air heats up, its density drops. Gravity then takes over, creating this powerful buoyancy-driven upward flow.
To simulate this efficiently, engineers use the Boussinesq model. It treats density as constant, focusing purely on buoyancy forces.
But here's the catch. That approximation only works for very small density variations and slight temperature changes within the room.
Let's take it further. Conjugate heat transfer mathematically tracks energy moving straight from a solid server right into fluid.
At a microscopic level, CFD mathematically couples the actual physical boundary of the server directly with surrounding fluid.
Right at this interface, temperatures match perfectly, and the heat fluxes are exactly equal and opposite. It's pretty wild. So how do we actually visualize all this math? We use tools like contour plots, vectors, and streamlines.
Take contour plots. When you see closely spaced lines, that means rapid physical changes in extreme thermal gradients.
Vector plots use tiny arrows at discrete grid points to show you exactly where the cooling air moves.
Then we have streamlines. They trace the fluid's exact path, which is absolutely crucial for spotting dangerous recirculation zones. As fluid dynamics pioneer John D. Anderson said, these graphics aren't just technical records, they're literally works of art.
Another clever trick is shell conduction. It uses virtual cell layers to compute heat transferring across thin metal walls.
Finally, to validate these simulations, engineers check the total heat transfer rate, ensuring a perfect net zero energy balance.
CFD literally makes the invisible visible. So what hidden thermal weather is shaping the systems you rely on today?